Rasmus, by the way. There's also a link here because I'm going to make a small questionnaires during the speech, so there's an online polling system here. I have a lot of, before I start, I would like to give my credits to my co-workers that have helped me a lot by producing slides that I have been stealing and so on. And I also nominated a little expert panel because I can definitely not answer all questions about this. So I have asked Christina. Christina, can you show us who you are? This is Christina, PhD student in the group. And Christian, where is Christian? He's there, also PhD student in the group. Patrick, where are you? All the way down there. And then we also have Anders and Medrana. Anders is in there. I think Medrana is online as well, and they will answer about questions about scannings. And then I've also a man I haven't mentioned here, Morten, who will also, he's there. So when you have fascinating questions, I will look blank and I will deflect the questions to my expert panels. But without further ado, I'll start here. So I'm an engineer by heart. So I make a requirement specification. So I made a requirement specification of the audience I want. So this is what I want you as an audience. So what's the ideal audience for me? So that is people who have a limited practical experience with geometric deep learning, that still have a good understanding of basic convolutional networks and probably have seen the unit before. And also you might come in a situation where you have 3D meshes, or where your data in a kind of a magic way suddenly turns into 3D meshes by, for example, ISO surfacing or something else. You might come in that situation, and then you would like to do something like surface-based classification, labeling, segmentation, shape matching, or something like that. So you lack a good starting point, and which approach could I go into? Which part of the jungle should I explore? And that is what I hope to give. So to see if I got my requirement right, I've actually asked a little questionnaire here. So please go to your telephone, your computer, go to this website, and then we can see, because then I can kind of calibrate my goal of the depth of the. But can't you see that on your phone when you get it? Oh, so it's the website you can't see.
We can't read anything on the whiteboard.
Okay, so okay, perhaps I can make that.
Yes.
Okay. So I can make this kind of walk. Okay, how many of you can see it now? Okay.
Rasmus,
Yeah.
why don't you open the chat and write it there?
Because it's not everybody who's online.
No, but if it's on the screen, nobody can see it.
Can't you also propagate it down? Okay, Martin can write it on.
I
have a limit for of multi tasks. So anyone still having problems getting in? Then. Is there any other problems we need to solve before I? In any case, it seems that quite a majority have a superficial knowledge about the field, which is a very good starting point. That is actually what I have. So what you can get out of my speech today is that you will hopefully get an overview of the different approaches to deal with 3D meshes. I'm quite specific that I say 3D meshes building on top of what I said. There are ways to use these methods to higher dimensional data, but I will focus on the 3D meshes and then you can generalize later. So you will also get an understanding on how this method works in different types of data, how invariant they are to different mesh properties, and also what are the limits for what they can actually do. Because compared to standard image processing techniques, there is a huge variety in the type of data that these ones contain. So let's also get a little bit of a feeling of what is your interest here? What is it actually you want to do? Are you more on the engineering part of it? Okay, 100% on the first one. That's interesting. I can honestly say with my background that I will probably cater most for that group. I will hopefully also give something to that group, but that is not my own strength. I will say I'm more here, but I still hope that everyone will get something out of it. So start by where do we get services from? I mean, they come from many different sources, and one of the most typical one is like direct surface scanning here. Here, this is a rather state-of-the-art 3D facing scanner. We have some colleagues here who've been scanning, so scan, and you see them in many different applications. This one is for aesthetic surgery, both for reconstruction, but also just to make people look different. And therefore they have an interest in having high accuracy scannings of the human head, including textiles. We could also have small object scanners here to the left. You can see one from the hearing aid industry, where they take ear impressions and make an accurate replica of the geometry of the ear. Probably one of the most scanned geometries in the world, but it's just not published very much because it happens inside the hearing aid industry. Then to the right, we have from our own lab, we have our object scanner here, structured light scanner. And this is a who was scanned by followers. And I guess it has a resolution around 150 microns and so on. Anders and Adrana would know much more about that. But just this is also a very typical example of a surface scan. Then there are different sources where you can also get surfaces from. You can have made the 3D classification of voxels and created boundaries of the different labels. So these kind of interfaces describe the kind of crude anatomy of, for example, the brain. And there is still a lot of anatomical knowledge in that. This is an isosurface from a MR scan where you have just taken the isosurface that corresponds to the iso level that corresponds to the skin to vacuum or air surface, and you can see there is a lot of noise here due to inhomogeneous in the field and so on. And also here you have a different structure where you computed certain types of isosurfaces and created a surface representation. So you also have artificial models where people are basically hand-drawn models, and they have another nature. They have another types of noise properties, and they have other invariances as well. So let's look at some important aspects of measures that you need to take into account when you make a choice. For example, what are the rotational aspects, the size, and the topology? Is it manifold, as Andreas talked about? And also about something about how it's sampled and what are the noise properties of the meshes. So let's first talk about the geometry and the invariance for that. So does it actually make sense to have a canonical orientation of the objects you're looking at? And does it actually matter? And yes, it matters. Some methods can handle it, some cannot. For example, these objects, you could actually say that they have a canonical orientation. There's a natural orientation of these ones here, because you can say a chair has a canonical orientation and so on. Probably also a face also have a canonical orientation, but when you come down to other anatomies or other shapes, it doesn't necessarily always make sense to have what we define as a canonical orientation. Or at least when you acquire them, you cannot assume that they are oriented in the same way, and that can be a major pain, or you at least have to deal with it the way you design your visual analysis. Then a little bit about mesh sizes. What do you see in the articles? A lot of the methods that we're using, they come from another field. They come from Andreas' field, which is geometry processing. And they like to use meshes that they can deal with. So normally they are not so super big, and they have some nice properties from an analytical point of view. For example, we often see articles that are published with meshes that have a few hundred vertices and a few hundred faces. While when we work with anatomies, it's often that we have hundreds of and thousands of vertices, and that has some other requirements for the methods. So then a little pop quiz for you. I have 3 of our meshes here, the 3 meshes here, and we would like to know, and you can talk together, you can talk to the person that's sitting beside. What are the topological equivalences of these meshes?
What's the thing on the right? Is that a hearing aid?
No, this is Christina, what is this?
This is the left atrium with the left atrium with the attachment.
So the question was it this? This is the left atrium of the heart, and this is a left atrium. So this is a heart. The thing to the right. The thing to the right is a scan here. So this we are seeing it from the part of the eardrum up to the outer ear.
Det er jo lidt åbent for fortolkning.
Halsen lukket.
Ja, halsen lukket af det der...
Jeg tror ikke helt an på, hvordan hullerne er. Jeg vil sige, det er en mulighed. Det ser ud som
Ja, du har ret. Det skal næsten det bedste. Uden, det er bare ikke mulighed. Det er ikke en mulighed, så det kunne være noget. Jeg kunne ikke den tube den til højre. Men det kunne også godt være, at Martin var en byste, hvor den var lukket i bunden. Jeg kan ikke se det. Så er det svært, jo. Det er ikke svært. Svært, det er tube. Fordi jeg tror, du er en disk, ja. Jeg var i hvert fald en disk. Så du scanner på samme måde. Og den til højre, den er tube, ikke? Den til venstre, tror jeg, er lukket. Så bliver det svært, det er tube. Jeg tror, jeg satte så bilen over. Han er tilbage.
This was a picture shot. Now you can correct it for that. But yeah, with the choice of the way we have been doing the cutting of these pictures, this is actually correct. And this is also a choice. What is the topological equivalence? What you're actually looking at? Here we have cut Martin's sketch, so this is actually a disk, which is makes sense, perhaps not makes sense, but does it matter? It does. So it is actually quite important to know what is your topology, because you can have, these are quite simple topologies, but you can also have certain situations where it's very complex. And this is, I would not say in Andreas' definition, this is not manifold. So, and it matters because the methods are vulnerable to these kind of different topologies, as these as the state of the art are now. So we also have another thing you have to look at. That is, how is your mesh sample? Is it sand equally all over the surface, or do we have these like Martin Cube type of artifact? Do we have Gaussian noise spread over the surface? Or do we have something which is much more nasty like this? This is really horrible when you look at it. But if you look at it from with a human eye, you can still see it's a human face. You can still see it's the chin and so on. While if you look at it from a triangle perspective, it's just a mess. And we also have to consider that you can actually have, this is a completely valid MR scan that has been isolated. So let's just take a little mesh and make a little biopsy. So this is a facial mesh from the BU3DFE data set, one of the few public facial scan data sets. It's a reference data set, and it's what you could call a mesh in the wild. There is for facial analysis, there's a huge topic called face in the wild. The face in the wild challenge, you have to look at the this group of people, and then you just do the analysis of face. You can use the old Viola-Jones methods and so on, and they're very, very robust to all kinds of background noise. And if you want to make something like similar to that in mesh processing, where you can take an arbitrary 3D scanner and do image analysis on that, you also have to take care of that. There can be a lot of different issues in that. So, for example, it looks perfectly fine. It's a nice face, but it looks also to be topological to actually a disk, not a plane, but it is not. It has flipped triangles and non-manifold parts like this, but it has complex noise issues and so on. So it also, the normal face has a canonical orientation, but when you put it into a 3D scanner, you cannot be sure that the face will always be placed in the same place always. And certain scanners have different coordinate systems and so on. So you have to take that into account here. So does it actually matter? And it matters quite a lot. It is equivalent to that if you have a photo where one of the CCD elements were dead, that your 2D CNN would crash and burn as soon as it saw it. A lot of these standard algorithms you see on the net, they will make a topology check on your surfaces and come with a really nasty error if it's not manifold, for example. So you have to think about if you can do that, do something about it. You can use Andreas methods to pre-process your mesh to clean it, but the problem is that you often need a specific method for all the different types of data. Depending on the nature of the data, you need a certain way of turning it into a nice list. So it is not trivial to do that, and sometimes you also smooth out the information you actually want to have in your data set. So now I want to make a little progress because I'm going into the more deep learning part and just want to have a understanding of where you are. Okay, it seems that at least the majority have a conceptual understanding of the UNet. So I'll start from there. So the UNet, this from the article here, is a classical segmentation network. You have an input image and the result is an output image where you have a pixel-wise labeling of your input data. And it's constructed in this U shape. So you have a down part that both do convolutions and you also do a resolution reduction, and then you upsample the net again. But I'll look at this part, which is in this context the most interesting. And what kind of basic operations do you need to create a path like that? And I would claim that the two basic operations you need is the pooling operation to actually reduce the resolution and make it equivalent to translations. And then you also need a convolution operator to actually do the machine learning part of it. So let's look at these two primary operations and how can we adapt them to our complicated machines here. So let's just come with a little conceptual head up. What is needed to do a convolution? You need to have data. You need to have some kind of graph structure connected where there is a kernel as well, where you have the learnable weights that can be put on top of your data. And then in your data for each node, you need to have some kind of element. Your data, that's an image. And then for each node, you also need to have some kind of associated, either a scalar or a vector of information. And for measures, that could be the local geometry, for example, while in a social network, that could be some kind of identification of the person that are the node in your data. And then you also need to have a neighborhood defined. How are the different nodes connected to each other? And when that's said, I will first go a little detour before I come back to how we can use this in geometric deep learning here. So I will cover, and I'll just give a conceptual overview of different ways of looking at measures in a deep learning framework. And I have to come with a disclaimer, I'm certainly not an expert in all the different gory details and all the methods. That's also why I have my expert panels, but with really hardcore questions about these methods here. So let's just look by a conceptually simple way to do this. So if you have a method, if you have an object, a 3D object, and you want to put it into a class, one way is to take the object and look at it from many different directions. And for every direction you look at it, you assign it a class. So from here, I would say, oh, this is a cylinder. From here, oh, I guess it's a coffee cup. Here it's a coffee cup, but here's a cylinder again. So I can look at it from 100 different views, and for every view, I will give it a class of my predefined classes, and then I can make a majority voting. And that is basically what they do in this multi-view convolutional neural network, which has been a kind of a groundbreaking method. It's conceptually simple, but there is a lot of devils in the details of it. So they do basically a 2D CNN where they look at different renderings of the object. They do a classification per view, and then they do a view aggregation. They do a way of a view pooling, and they don't necessarily just do a maximum voting or a kind of consensus voting. They actually put that into another CNN to actually make the class, to have most probable class here. So this is a core method, and they have used it for object classification based on, you could say, 3D models that are shape net models. So it's mostly geometric models of things. And they do it by sampling around the object, and they have a fixed view where they do the rendering. And they have two approaches, one where they just put this ring of cameras around it. So, yeah. Ring of cameras around it, and then they also have one where they make a whole sphere around, where they then take photos of this around the object here. And they also do use pre-trained networks to do the classification here. So there's a lot of the very heavy stuff from the 2D methods that they can use in this approach here. And they, at that time, got super nice results on the classification of the shapenet. So you say it's a way of cheating that, because you're actually not doing anything 3D, you're just rendering, but they still get impressive results here. And my observations and our observation is that if you can render your object, you can do the analysis. And that's a very, very strong point, because with modern rendering hardware, you can really render nearly everything, even very, very ugly surfaces. Of course, if you have things that are covered by other things, you have to think about translucency and so on. But it is still a rather robust method to having all these kind of nasty meshes you can have in the file. It requires that you have a pre-alignment to a canonical orientation, because the views are pre-sampled. If you want to have it rotationally invariant, you would need to sample a lot of other kind of configurations of your camera, which is very close to kind of modern heavy data augmentation. So it's not a very super elegant way of doing it, but you can adapt it to your data. So we have made a refinement of this method. We have used these ideas in another context where we wanted to use a multi-view method to predict fiducial markers, landmarks on 3D places here. And the way we do it is that we adapt methods that are coming from post-tracking, where we, for every landmark, create a heat map, which is a probability distribution that have the most probable placement of that landmark from a 2D point of view. And then we aggregate the results from many different views into a common consensus for every landmark. So we are using the 2D methods to compute 3D positions. And here's a little overview of what we're doing. We have different renderings. We also do both RGB rendering, we also do depth map rendering, and we do geometry rendering, and we also do what's kind of a depth map rendering here. And then we have something, what's it called, not a UNet, but an hourglass network, which is a kind of a unit architecture for that. So what we get out of that is from every view we render, we get a set of landmark positions. And if you look at the camera geometry, because we know the camera we've been used to render the images, we know the camera geometry, and that's why every landmark corresponds to a line in space, and therefore we can kind of gather all our views into one. And then I have a little question here. So I have all my views, and then there is something called ransack. And what can ransack do for me in this situation? And you are welcome to talk.
This is ude. Og træer, eller den sidste her er også ude.
Ja, det.
Man kan sige, at et sample, hvad gør det? Det er ikke nogen konsensus med os. Det må være den næste. Selvom man har dygtigt beskæret, det er ikke helt op.
Okay, let's see what you think. That is super nice. So ransack is a method from when I was a little girl, and random sample consensus, where you can robustly, for example, solve least squares problem and remove outliers. It has been used in classical machine learning a lot, so we thought this is a nice idea. So what we use it for is that when we have all these view rays, and because we also see, we render our faces from directions where you cannot see the landmarks here, some of the landmarks will be way off, and therefore it's very important that we can also, when we do the d-squares estimation of defined points, that we have a way to detect outliers. So that was what we used to kind of propagate, aggregate the information together, and therefore creating very robust facial landmarks. And as machine, since it's a rendering-based method, we can also handle surfaces with a lot of really, really nasty noise and robustly place landmarks. So we have trained the method here on another type of data, and then we can propagate it and use it on nice surfaces of the mask. So in that field as well, when you look at,
Rasmus, what would you say characterizes these landmarks of the face? Some of them seems like curvature singularities, but not all.
But yeah, so there are like, I would say there's like 3 types of landmarks that we use in this characterization. There's anatomical landmarks with the tip of the nose and this intersection here, which basically have anatomical names. Then there are what I would call mathematical landmarks, which is characterized by a place where there's a high curvature. And then there are some that are just placed with a regular interval between 2 anatomical landmarks. So these ones are by far the hardest ones to set because they are not having a kind of a clear anatomical definition. So these ones are in literature. If you look at a facial landmark precision, these ones are the ones with the biggest accuracy. Of course, then you also have some that are very influenced by anatomical variation, for example, the ones in the mouth that are placed here, but because people have so many different facial expressions, there's a lot of variability. And of course, these ones are super hard because they are also just more or less placed if there is an eyebrow or not. Yeah, so we placed these landmarks. We had an inter-observer studies years ago where we had several observers placing landmarks and looking at the intervariability between different landmarks. Okay, so another way you could say where you go from the transition of having classical rectangular CNNs to the geometry is this one, where you take your 3D shape and then you make what's called an occupation sequence. So you say there's an inside and there's an outside of the object, and then you create a binary volume that crudely represents your object. But what's good about this is, of course, you can use a standard 3D convolutional neural network. And as it can be seen in the article here, they use a 30 times 30 times 30 occupational grid. And this is, of course, limited by the GPU memory. They got decent result at that time, so it was an approach that definitely had its own benefits. But the problem, of course, is the enormous lack of resolution. So they also did something where they also tried to get over this with the canonical orientation by taking and looking at the object in different poses and then making some kind of aggregation of pooling of the different orientations and seeing what is the different classes or the final class coming out of it. So again, it also have problems with the pre-alignment. It's not really rotationally invariant. And then, of course, you also have a massive loss of information. And that's also something you have to look at. Are you just interested in the global shape of what you're looking at, or is the fine details interesting for you as well? And that also brings me to this, where you can classify your method into what in broad sense is called extrinsic methods or intrinsic methods, where the extrinsic methods, you have your object here, which is the tube here, and then you have a representation that only indirectly represent the object you are looking at. A little bit like, or very much like the implicit surfaces that Andreas introduced here. And then you have the intrinsic, where the structures you're looking at is following, in a rough sense, the object you're looking at. And now I'm getting back to the convolution because I'm changing a little bit back to the intrinsic methods. So what is needed for performing a convolution on a mesh here? And just a little pop quiz again. So if you look at a mesh, and now you look at the edges, for a standard mesh, how many edge neighbors does an edge have? I remember an edge is the ones that connect two vertices. How many vertices? How many edges does one edge has in its wrong ring neighbor? And you're allowed to talk to each other if the questions. Don't panic if you don't know the answer.
Så jeg har altid været wondering omkring et vertex. Jeg tænker, at den er to trekanter, der deler kanten. Det har jo været to andre kanter, for at få det være også fordi de skal have et solidt svar.
Ikke sikkert, så one ring neighborhood.
Jeg tror han mener one ring er de to trekanter her. Så har en hver to kanter, ikke? Så som men når jeg hører one ring, så tænker jeg altid på det som rundt omkring et enkelt vertex.
Ja, det kan være rigtigt.
Det kan have mange forskellige antal. Men det skal være et bestemt svar. Jeg tror det. Jeg er ikke sikker på, at alle er helt enige eller klar over definitionen af one ring.
Okay, so when I'm asking these questions, you should not panic if you don't know the answer, because it's a question of me also to kind of calibrate what I'm going to say, how much I should actually explain. So here you have, we assume you have a triangular mesh. And as Andreas said, when you have a vertex, the balance, the number of spokes that comes out, the number can vary over the mesh. You are not guaranteed that you always have 6 neighbors coming out from here, unless you have a completely ideal mesh. And you said it only happens in a donut or in an infinite plane.
Yeah. Anything can happen in a donut in an infinite plane.
Yes. And we don't want to be concerned about it. But if you look at it, instead of look at vertices, but look at an edge here. They always have what we call the one ring neighbor is the ones that just are here. So we have this one is a neighbor, this one is a neighbor, this one is a neighbor, and this one is a neighbor. So we have always for an edge 4 neighbors, and that is an important information if you want to make certain types of algorithms that are dependent on the number of neighbors.
Hvorfor har I ikke 8?
Og den kaster lige over som plads. Den tager vi bag. So let's assume that I'm right. And now I'm going to talk about the first method that do what I could call convolutions on meshes. And I would say that the expert here is Bastian. So when you have questions about this, then I will deflect some of them to him and also to Christine. So mesh CNN is a recent method that have gotten really good results on the reference data set. And what that is, the goal of this one is to do a labeling per edge. So when you have the shapes, you want to assign a label per edge. So it's not looking at vertices, it's looking at edges, and it assigns a scalar to each edge, which is the class here. And one of the core methods that they're using is a reduction of the mesh, as the Garland-Heck method that Andreas was talking about. And they use that as part of the pooling operation. And let's just go back to what are the requirements for having a convolution. It means that per node in your graph or in your matrix or image, you need to have some data that describes what's there. And what we're interested in is the local geometry, because we want to have something that classifies based on the shape of the object. You could have many other things. You could have a texture, you could have a person identity, but here it's the local geometry. So here they have a geometry descriptor, which is based on the dihedral angle, the 2 inner angles, and the edge length ratios of the neighboring edges. And when you combine that, when you take these values and you combine them this way, you actually make a descriptor, a local descriptor of geometry, which is invariant to translation, scaling, and rotation, both locally and globally, which is a very strong point compared to some of the other methods that where you had to have some kind of canonical orientation of your object here. So now we have a description, we have some values that we can assign to each node of our graph, which describes the local geometry. And then we can actually propagate these values together. We can concatenate them into matrices, and we can actually group them in a way that we actually create standard matrices where we can then use standard 2D convolutions on these matrices instead of trying to invent a new on the mesh operation here. And so that is the convolution part of mesh CNN. And then, which is kind of actually the more tricky part here, is how do we do the pooling and unpooling? Pooling, to kind of repeat that, is a way to decrease resolution, to make your method multi-scale, and also to make it invariant to translations here. So the pooling is actually an edge collapse, which Andreas produced. And what happens here is that you have the original mesh, yeah, and then you collapse the edge. Here, this one disappears, and the B and A becomes 1, and the C and D also becomes 1. And then you also take the properties, the geometry values, and you pool them together as well as average values. There are many ways you can pool, you could also take the max and so on, but in this, they have chosen to do the average. And as you can remember from the UNet, you have a down path and you have an up path. So to be able to do the up path, you need to have a bookkeeping system for doing the unpooling. You need to be able to unfold your mesh again, to to be able to propagate the learned values to the upscaling of the mesh. So therefore, you need to have a bookkeeping system that is a symmetric variant of your pooling, which is kind of a unpooling system. And that is, there's a bookkeeping matrix here that keeps track of these operations. And again, I have to say the devil is in the detail. If you read the paper, it's nice and elegant. And then you try it with your own data and it explodes. Because why? Because the bookkeeping matrix is the size of edge time edge. So if you have 1,000 edges, the bookkeeping matrix becomes enormous and you cannot run the algorithm. They don't state that very clearly in the article. Because they use it on certain types of shape, which is very good at this. So just to show a little bit about their network, it's very similar conceptually to the UNet, and they can do that because now they have the basic operations. I know there are a lot of other types of operations you put into it, like batch normalizations and so on, but these ones are the primary ones you reproduce like the UNet in this context. And this is our students that have made this, where they have actually also made a unit architecture. So you can see that you have the down pooling here and you have the convolutions here. And we have used it for the classification of our complex heart shape there. As you can see in the original article, they get excellent results on the data that they're using it for. That's also why it's attractive to use it, because they're sure that it actually works. And here, what you can see here is an example of the down pooling example. There are some observations when you have these types of methods. It gets impressive results. It is invariant to these geometric transformations. Unfortunately, it is in its bare bones version limited to smaller meshes. And then it's also, and that's something you also first figure out when you're sitting with fingers in the dirt, it is very vulnerable to mesh topology. If your mesh is not manifold, it will give you unreadable error messages and so on. And it can also by itself create non-manifold parts in your mesh because of the way it does the down. So again, we are still in a state where most of the state-of-the-art methods, we have certain requirements to your mesh. We have, led by Christian and also with Christine, created a sparse version of mesh CNN, where we have also put what's called an attention block into the architecture here. And the goal for us was to have these complicated heart structures here, which is the atrium. And we want to separate the atrium from the left atrial appendage, because this is where blood clots form and can propagate into the brain. And to avoid that, there is a surgical procedure where you put this kind of little umbrella through here, up through the heart chambers and into the left atrial appendage. And they are very good at that. The visual detail to close this area here, so we don't have the blood clots coming out of this place and out into the brain. The problem is that now when they have to design this operation, when they choose one of the many devices, the size, they're looking at the CT scan and it's like this, or they 3D printed fillet with small iron balls, put the implant in and then shake it to see how many balls comes out. They actually do that to see what's the leakage and so on. So we wanted to see if we could help automatically delineating the structures and being able to just look at the cross-sectional area, for example. So that's why we're interested in trying to do these kind of mesh operations on type of complex meshes here. So what especially Christian, he pioneered was to turn the size requirements from a squared in terms of the edges onto a sparse matrix, and that required certain types of bookkeeping operations that was not trivial to do. So we have made it so it can work on much larger matrices as well. And we put the attention block, and I won't go into attention, which is a super hot topic now, but we can also use that for these kind of operations. So the hybrid methods in mesh CNN is one way to approach this about creating convolutions on mesh structures. There are also other ways, and I've just been to this library called Hydroc Geometric, which is one of the libraries that where you can actually do deep learning on meshes. So just taking a screen dump of the current number of convolution operators they have for meshes. So as it can be seen, 2D convolutions, there's not super many dilated convolutions. For 3D is something completely different. And I'm going to explain all of them. I'm not, but definitely just to have an overview of there are a lot of different approaches to doing this. And the same you can say with pooling here. There's also a lot of different ways to handle pooling. I mean, the collapse, how to collapse mesh entities into smaller groups. And from this review paper here, which is an OK review paper, they have an overview of other ways of doing this intrinsic way of dealing with mesh convolutions. A lot of this is pioneered by Michael Bronstein and also partly by his brother. And one of, you could say, main observations is how do we weight the local neighborhood? Conceptually, you can see that it's a question of defining a neighborhood on the mesh and then having some kind of kernel with a certain shape that you then use to do to actually do the convolution here. And I'm going to a little bit into detail to one of the approaches here. So just again, our little convolutional heads up here, you need to have a neighborhood, you need to have some data, you need to have your kernel and so on. And what you saw here before, these structures here are kind of different kernels. So they are a mixture of different sub-functions that can be defined in different ways. So a lot of the difference between the recent methods in that school, I would say kind of a school, is a question of how to define the kernels here. If it is oriented or anisotropic heat kernels, a little bit like Andreas showed, is it a kind of a heat propagation function where you look at a little bit of a heat curve, isocurves in a heat function? Is it a mixture model of different Gaussians and so on? So that's the kernel shape. Then you also have the question of what kind of data do you have per node? What do they actually describe? And that's where they, at least the Bronstein school, they kind of generalizes what kind of data do you have for a graph? Is it something that is a topological descriptor, a geometric descriptor, or is it something that describes a social network and so on? So I will only go into the geometric part, but quite a lot of these methods can generalize into handling other types of graphs as well. But let's so one of some of the major methods, difference between these types of methods is how is the neighborhood computed or defined, and what are the values that are actually used per node, and how are the weights in the convolutions defined. And an even bigger issue as well is how do we actually deal with rotational invariance here, because you can see they also define the neighborhood, and here they have defined it in a polar coordinate system, so you actually have some kind of rotation around here. And I'll get a little bit back to that. So let's just look at one example, the MONET, which is one of the very recent methods from the Bronstein group, where they get really impressive results on certain types of data here. So to apply a convolution on a mesh, they define a local polar coordinate system here, where they define an implicit up direction. You need to have that in a polar coordinate system. And then they have a local weight matrix, which is kind of like your convolutional kernel. It's just defined by some other basis functions that you then convolve with the underlying data. And the way that you put these two together is quite similar to the functional mapping that Andreas explained, or the exponential mapping. I won't go into much of the gory details there, but just a lot of the mathematics that Andreas explained also about the Laplace-Beltrami operator is also used to computing these kind of heat-like functions over the meshes here. So one thing that surprised me a little bit was that in the papers, they don't go very much into detail, but what is it actually that we are looking at? What kind of description of the local geometry are we actually looking at? I mean, they really do a lot of different approaches to do the convolution, to define the mask here, but the underlying geometry, they only kind of mention that in a side kind of paragraph. And it actually turns out that the way that define the data per vertex that defines the local geometry, they use something called the local shape signature, which is a histogram of local normal vectors. And then they generate a 544 dimensional vector per vertex that then describes the local geometry. And when I saw that, I thought, that is Belongi. And why do I say that? Do you know why I say Belongi?
Histograms of orientations, shape index.
Yeah, shape context, yeah, actually.
Context, yes.
So our now very good colleague, Sars Belongi, I saw him at a conference when I was very young, and then he I actually saw this presentation, shape matching and object recognition using shape context. And that has kind of revolutionized the field, and it has many thousands, 20,000 citations. And what they used was that they wanted to match complex shapes with a changing appearance consistently. So how do you match, how do you register objects like this that can really be very different in appearance? Well, one way to do it is to create a local description of the local shape and then do a matching of that. And they've defined a new type of description, which is a polar description of the local point. So you have one point here, and then you look at all the other points, and then all the neighboring points you put into a polar coordinate systems like that. Every block in this polar histogram here can then be mapped into a 2D histogram. So what you have here is a shape descriptor that describes the local shape around a point. So for that, you can create a local descriptor. And then the second trip that they do is that they do an assignment. So you have one shape that for every point has local descriptors. You have 7 similar shapes that also have local descriptors. How do we create a description here? They use a specific algorithm. Who knows the name of the algorithm? It's a country.
Okay.
The Hungarian algorithm, yes, they use an assignment operator, which is a one-to-one, you force a one-to-one correspondence. So the two things together became a really strong cocktail to match shapes, and that was really a big thing now 20 years ago. And for the last 15 years after that, people tried to generalize that into 3D as well. And that is actually what they have done with this shot descriptor. So the shot descriptor is what they use in the Bronstein school to describe the local geometry. And that, of course, should be a geometry descriptor that is good enough that you get every detail you want. And one of the reasons why it's super complicated, why the shape context has never really been big in 3D, is that you're losing the local reference frame. When you have a 2D object, you only have 1 degree of freedom of it. You have the translation aspect, but mostly you have the rotational aspect, which is a little bit complicated. But in 3D, you have a 3D lack of local reference. You don't need a local, you simply lose the local coordinate system. So suddenly you cannot match one descriptor for one shape that is computed here. This is completely the same anatomical shape, but the local reference frame is completely, the local coordinate system is completely different. And therefore, the two local shape histograms are completely different. So you don't have this invariance here. So there are different solutions. And just to come with an equivalent, imagine that in your 2D image that you have no local reference frame. That would mean that when you're running your 2D convolutions over your shape, that it would basically wobble like this, and you would have two completely similar anatomies, but you could not compute a shape here or a convolution here that would be similar to this one, because the two local reference frames are completely different. So there are ways to deal with this. One is that you simply do a convolution all the way around, that you simply rotate your kernel 360 degrees, and you take the maximum output that creates a certain types of rotational invariance. That is seen quite a lot of papers in 3D that they actually say that they take all the different rotations around the normal vector. Another way that you could actually do it is that you follow that you actually your local reference frames follow the local gradient. So suddenly here you would have probably you have your local reference frame like this. They would all go like this, following the ear, and the same here. That could be good, that may be bad in a way to create rotational invariance, but definitely that's actually what they do quite a lot often in 3D, that they compute some local differential properties of the surface, and then they create a local reference system to compute the features. And again, this is about computing local features that you can then use for shape characterization. So it's very important that they are consistent, even though your geometry changes a little bit. And one way to compute the local differential properties is that here you have your 3D shape for your given point. You take a local neighborhood, you sample local points here, and then you can do that more or less smartly. You can even just take the raw vertices lying within a sphere. That is not very good for very thin surfaces, because then you can get points that are on both sides of the surface. You can also take geodesic neighbors that follows the surface and so on. There's a ton of different things to that. But just assume you have sampled points in a local neighborhood. Then you can do an eigenvector decomposition of these points and create a local reference frame. By default, the least you have 3 eigenvectors. The smallest one is an approximation of the surface normals, and the 2 others, they will follow the surface. And of course, if you have a ridge, one of them will probably lie on the ridge and the other one will not, and so on. The problem with that is it's normally very inconsistent and ambiguous, because when you do an eigenvector decomposition, you cannot be guaranteed which way it points. So there are different ways to solve this, and this paper here say they have created one way of solving this ambiguity by propagating like a coding system all over the surface and so on. And as far as I understand it, that is actually the way they orient the local geometry description in the Bronstein papers here. So this is one of the things where if I had to, and I have not, would re-implement one of the Bronstein's method, I would say, I need to try this first to see how consistent are these description of geometry compared to the geometry I have. Especially if I look at very noisy surfaces, how consistent can I actually make a geometry description that is, if I propagate it over a shape, like similar shapes, but have different sampling, are they actually consistent and so on? So, but that's just a little advice. Good. So again, impressive results, but try to look into the details about how they represent the underlying data. And also, do they have topological constraints and so on? I have not tried them, so that's why I cannot really come with any personal horror stories. So again, then has also been a lot of focus on spectral methods, and as Andreas also showed, there's a very strong correlation between Fourier analysis and also the Clausians and how you do convolutions. Probably quite a lot of you know that you can do convolutions in Fourier space, and there's a certain benefits about that. There's also been a lot of spectral methods for meshes developed and published, but it seems that they're losing popularity, and therefore I have chosen not to go into detail with them. And there's quite a lot of comments, and also in the recent Bronstein papers, about the shift away from spectral methods or going into more local approaches to the spectral methods. So now I'm going back to some of the more extrinsic ways of representing meshes, because as I can say, we're going a little bit forward and back to different representations. And you thought that deep learning on meshes is only about the intrinsic methods. I would say that the state-of-the-art method, they are going in both directions as well. So Andreas briefly mentioned another way of representing meshes, which is an implicit representation, for example, here, where you have voxel grid. And for each voxel, you have a side distance to your surface, and inside or outside, and then you can use Martian cubes to get your another fancy measure as advocated for to get your surface back again. The interesting part about having these implicit representation is that it actually also carries information about the shape further away from the shape itself, which can be useful in quite a lot of other situations. For example, in shape matching, where you actually can drive the source shape to the surface shape, because you know that you are close to the target. A very recent method, which has also gained a lot of popularity, is called DBSDF, Deep Signed Distance Field. So it's based on this signed distance field representation of surfaces, and it's in its core a very simple network that, just given a position, can predict the signed distance to the object in question at that position. I would say Christina is a local expert here, so she's the one that to go when you have intricate questions about this. So if you look at a single shape representation, if you just have one single shape you want to represent with your deep learning network, then you can give it a free position, and then you have a neural network here. And that are different architectures that can be used. But what it can do is that it can predict a distance to the surface in this specific point here. That's not super interesting. The more interesting part becomes when you actually have a latent vector. And now I haven't made a question, but if I say latent vectors and latent vector spaces, how many of you are used to navigating around or using a latent space for something? Okay, quite a lot. I mean, conceptually, you can consider it as that if you have made a PCA analysis and you have your PCA scores for a data set, then you can look at your PCA scores in a reduced dimension space and make classification in that. And while the latent space is typically a nonlinear space, but conceptually you can consider it like that. Here, we start by having random latent vectors, but you can also assign them classes. And then it's a self-learning algorithm that then optimizes both the latent space and the positions at the same time. And it's only a decoder, it's not an encoder. So conceptually it's similar to when you have a UNet, you don't have the compression part, you only have the expanding part. Isn't that correct, Christina? Something that is good. Which is also the interesting thing about this type of looking at it. And when you train it, you do it in a funny iterative way where you both train the decoder by giving it ground truth and also giving them then these the latent vectors that are then being optimized at the same time. And the point of having this is that you can make global shape classification using this implicit representation of the shape. And in that paper, they have a very impressive results by having what's called shape completion, because they now have an implicit representation of different classes. And then they can get a partial part of a shape, which is then sampled in a distance field. And because they have this implicit representation of the entire shape space, they can then reconstruct the entire shape based on that in their implicit way. So the way that they then have to reconstruct is that you need to have a measure, like for example, Martian Cruiser and that's fancy method, to get it out from the reconstructed distance field, because this one is a distance field synthesizer. This is what we get out of. So some observations about using this method, which is very strong. In that method, you need to be able to compute a signed distance field. That's why by default you need closed surfaces, else you will get weird artifacts where it's not closed. It's not particularly rotational invariant. It assumes that you have a canonical direction unless you do heavy data augmentation. And then we can use it for shape qualification, shape synthesis, and shape completion. I don't know if it can actually be used for labeling as well, but then this is definitely what we have been using it for. There are other ways of dealing with implicit representations of surfaces, and this is just a little overview. I mean, where you also define other types of basis function on a grid, for example, and then can do convolutions. I want to finish off with our recent paper that was accepted at MICAI. Congratulations, Christina, which is on a kind of another representation, which is an unsigned distance field. When I say unsigned distance field, it sends shivers down the spine of Andreas. And why does it do that?
You want me to answer?
Yes.
Well, it's just very much more difficult to find the surface when it's an extremum than when it's a sign crossing, right? Yeah, that's why. So
we have still chosen, even though Andreas said, and it is complicated. I mean, because when you do the meshing, when you want to reconstruct your shape based on your implicit representation, what Martian cubes and other meshing methods do, I have to. Now, next time I say Martian cubes, you just imply that there is a better method. So it looks at sign changes, and so it places the surface where there is a plus and minus. But if you have an unsigned distance field, you have a minimum. And even there, you get into Shannon's sampling theorem that you suddenly requires the double at high sampling and so on, because of all these complicated things that would have two boxes and so on. It is just not trivial also to find the intersection or actually to find the minimum that you have to measure it. And we have some usable ways of doing it, but we're not really there yet. But the good thing about using on-site distance field is that they can represent arbitrary topologies. In the same shape space, in the same latent space, we can represent shapes that have a disk topology, a tube topology, a spherical topology, without doing any kind of code hacks to be able to adapt to these different topologies. Because it's an unsigned distance field, it actually handles the borders of the mesh nicely. And that is not something that is trivial normally to implement. So that's what we think is important. So this is our trained model and how it can both take, this is the train shape and this is the reconstruction, I mean the synthesizer that will synthesize artificial shapes in our shape space here. And these are some results, this is from the unsupervised classification, isn't it? Yes. So here we have just to show the expressibility of the method. How does the unsigned distance field work? And how does this latent space optimization work? How strong is it actually? Then we have fed it with facial scans and left and right ears, and also these heart structures. And then we have made an unsupervised classification. We basically said optimize your latent space the way you want it. And by just looking at the two PCA components, you can see that it has actually managed to classify automatically these topologies. People would say, oh, but it's very easy to see the difference between an ear canal and a face. But the point here is that we can actually represent them in the same space and actually also do the shape classification. So we think that this is a kind of a nice evolution of these types of implicit approaches. And that's it. That was actually what I had for you. I have a little bit some few observations. So if you have data and you have data that could be turned into these type of measures, what should you do? I think you should be very careful looking at your nature of your data. What is the number of samples? What is the number of registers? How much can I actually smooth it before they lose meaning? What is my noise properties? What is the goal? What do I actually want to do? Do I want to do classification, completion, matching, segmentation? And then you have to do the huge literature study. And then you also have to really look at the devil in the details, because it is not trivial to get a geometric deep learning framework up and running. It has a completely other scale of complexity than having a pre-baked network, because you need to have a mesh handling loader, and it's still in its infancy. And there's a lot of technical issues, like just if you're a Windows user, some of them can only run on Linux and so on. So it's still, there's a huge amount of research going on, but the learning curve is higher and you have to invest much more time. So it's very important that you choose a few of the right methods from the start and don't spend a lot of time to get something running where you, after looking the paper again, can find out it cannot ever handle my message because there is a vertex in squares memory requirement. And then what if I'm just more interested in the theoretical research direction? So again, this is really for the very junior of you. It's very important that you find a niche you want to explore and also try to find a competitive advantage where you and your group and your colleagues have a kind of a new view on what's going on, because there is a lot of things going on in this field. It's a super interesting field to follow because there is a ton of publication coming out. There's a lot of attention coming out. There's a lot of data coming out. But also just looking at high geometric, just a new way of doing mesh convolution probably won't get you into a very high-end publication. So it's also a question of thinking about what is it that I can really give to the scientific community based on what I already know. So that's it. And now we are ready for questions.